Okay, so in this session we are going to be doing the ordinary differential equations. That's the odds, right? Okay, so let's just kickstart with what ordinary differential equations are. So the definition for an ordinary differential equation is just like a function, right? That relates, or it's an equation that relates a function of one variable to its own derivative, right? And I'll explain that later on. So if you have something like this, right, it's an ordinary differential equation. So you have a particular function. So let's say the function will be, let's say y of x, right? And then we are relating this function to its own derivative. So this is derivative, and this probably the function somewhere. So that's an ordinary differential equation. Right. Okay, so we have many methods of solving ordinary differential equations. We have the Euler method, the multi-step. We've not done this actually. We have the predictor corrector and this one too. We've done Taylor series, yeah. So this is a method. Implicit method. We've done this somewhere in differential equations and calculus too, yeah. And Ranjikata, we'll do that later on. And then finite elements method. We've not done this too. So that's the major ones: Euler, Ranjikata, and then Taylor, and then the other methods too. Okay, so we have different types of odds, right? So you can say types of odds. That's ordinary differential equations. We have linear, we have non-linear, and we have stiff, right? So we'll talk about linear and non-linear, but we'll not talk about stiff. This is a little more advanced. Okay. So let's get to yeah. So the concept of dependent and independent variables. So for instance, let's say you have an equation, right? So something like f of x equals 2x plus 1, right? So in something like this, it's not an ordinary differential equation, but then the main idea is that the dependent variable is always the variable that changes no matter what happens, right? So this one, the x, right, the x will always be the independent variable, right? So this is independent variable, and then the f of x will be the dependent variable. So that's just the whole idea. So when you come to here, right, so something like this, okay, I think with the independent and independent variable, dependent and independent, we'll show an example. I'm moving on, so you understand that more. Okay, so what are some of the applications? These are possible OBJ questions you can ask, since the exam is going to be OBJ. So we have population studies, so demographics, plant population, animal population. We have radioactive activity. So this, since it's like variable change, right? And then we have projectiles. We have other motions. Yeah. So basically, differential equations are for um, quantities that are changing, right? Changing quantities with time. So you can talk about temperature and all of that. Okay. So let's say you have this is an example from the slide actually. It was a parachute, a guy on a parachute, and then they want you to. Okay, so they just give the function of how fast it's moving with respect to time. So over here, you realize that your t, right, is your independent variable, right, and then your v is your dependent variable, or better still, your unknown variable. Yeah. So that's just how it looks. So your t, the time is independent. It's time would move regardless of what's happening, right? And then the velocity. So just say that we are trying to find the acceleration, but then it's velocity with respect to time. So the velocity becomes the unknown or the dependent variable, and then this one is the independent variable. Just say that way. Yeah. Now we have others, like orders of differential equations. So we differentiate between an order and a power, right? So order and power. These things are different when it comes to ordinary differential equations. Now, if you have something like this, right, the order of this is 1 because there is 1 here, right? And then the power of this is still 1 because there is 1 here. I hope you are getting what I'm doing. Now, this one, the order of this is 2 because there is 2 here, and the power of this is 1, right? Yeah. the order of this is 3 because we have 3 here. So this is just like how many times are we differentiating? What's the order of differentiation? So here we are differentiating twice, right? So let's say if we had something like x power 4, right? And then we apply the 2x with, let me say whatever, with this one to it, or let's say another function is something like this, right, to it, then we won't just differentiate it once, we differentiate it twice. So you have something like 4x cubed, that'll be your first one. Then if you differentiate again, you have 12x squared, right? So this will be the second order differential. Yeah. So this one, to though the order is 3, the power is still 1. This one, the order is 2, right? So just see where you have the order, and then the power is 4. So these things are different, right? Now let's see where they apply. Okay, so conditions for having a linear ordinary differential equation. So now the order must appear to be in 1 power, so it should be just power 1 to be a linear ordinary differential equation. All derivatives are functions of the independent variable, right? So the derivative you are having, right, they should, so let's say I have a function of, say, dx of t dt equals something like, say, x of t, right? If you have something like this, then I should not be having another differential, let's say y prime of t inside here, right? Then this would not make it a linear ordinary differential equation. And then we should have no products, right? So better still, you can have say maybe y of t dot this, right? You cannot have this. It won't be a linear ordinary differential equation. Yeah, so this no products of unknown functions, right? Functions, and or is derivative, so you cannot do products there with the linear. So these are examples of the linear, right? So if you have dx of t dt, then this is linear minus that, right? So this is linear because it satisfies the theory. So first of all, the power of the differential is 1, right? Like I explained earlier, the power of this is 1. The second one, all derivatives are functions of the independent variable. This one is a function of just the t, and then we have e power t. Now if you have something like this, right, equal to, say, 2, this one is still a linear ordinary differential equation. The thing is that not, it doesn't mean all of these three conditions should be there, right? But none of these should be violated. That's what it all means. So you have dx of t dt, right, equals to, it's still a linear ordinary differential equation because it has 1 power, and then, or it doesn't have any other functions though, but then it's still correct. There are no products, so that's just right. So this one is ticked. If you have something like this, I think you've already seen why it is not a linear ordinary differential equation, because the power here is 2, right? Yeah, so this is the only thing that disqualifies it. Now when it comes to non-linear ordinary differential equations, you have higher powers than 2, okay, say than 1, so you can have 2 to infinity, right? Okay, let me say approaching infinity, because you can have infinity, right? So from 2 approaching infinity, then you can say these are higher powers. You can have product inside, so you should have product, you should have high powers to classify an ordinary differential equation as non-linear. Now these are examples. So you have the x of t minus cos of x of t minus 1. So something like this is non-linear because you have one function multiplying another function, right? So you have cos being a function of some other function, the real function we are working with. Something like this is not a non-linear. Why? Because it basically does not satisfy. So the powers are not high, right? There are no products inside. So if I had so something like this, you can classify it as, see the difference here, you have x of t inside here, you just have t. Now this is a function of just the variable, but then this one is a function of the variable. So this is why this one is not a non-linear. So this is basically a linear, right? If you bring s of t here, then it fully becomes non-linear. So I hope you get the difference, right? Okay. Now, what are the solutions you can have to an ordinary differential equation? So let's just list some. So we have separation of variables. We have integration factor approach. So I'll explain these ones. But then this one, remember we had I from our differential equations class. That was last semester. We have homogeneous and non-homogeneous. I can say this one fits here, right? We have variation of parameters. Yeah, there is like a directive of finding it, like just fixing in, altering the parameters to get what the function is. We've not done this actually. We have eigenvalues and eigenvectors. We've done this, and then Laplace. So some of these things were not done this semester, but then basically we've done them somewhere. Yeah. So how do we solve this? Now, in class we solve this using one finding method. So we're just going to solve this again, right? Using separation of variables. Okay. So let's solve this using separation of variables. So we have. So this one means you have to remember what you did in differential equations. Okay. Okay. So first of all, with separation of variables, what you need to do is that you need to separate the. Okay. Let's say you have to separate your variables. So what variables do we have? If you have the t here, we have x of t, we have x of t. So we want all the x of t's to come to one side and then all the t's to go to one side. Now here clearly we cannot factorize out x of t, right, and have like it's not possible, right? Let me just write it here to show you what I mean, right? Now we cannot do this, okay? This is not acceptable anywhere, right? Now this is not acceptable. You can be arrested for this. So so we did this one, right? So to solve this one, let's first take this one to the other side. So I have the x of t, the t equals negative x of t, right? Then over here what you can do is that you bring this here and bring this down, right? So you can have the x of t equals negative dt. It looks like we are getting somewhere, right? So with this you can now start your integration. So you apply an integral here, integral here. Mind you, the integration you are doing is indefinite integral, so you probably have to bring a c somewhere. Now integrating this thing, just try to remember from your this one class. If you have the integral of dx on x, right, then this gives you ln of x, right? It's the same thing for this. So we have ln of x of t, right, equal to, if you integrate this, you get just negative t. Now you can take e power both of sides, right? So you can just take e, yeah, just the inverse natural log, and then you have, so e power ln will go off, then you have x of t equals e power negative t, right? Yeah, so this is basically what we have. Yeah, so this is the solution to this linear differential equation. Okay, so with this one, if you want to, let's say you want to fit in the things, right, and solve them. No, I think that's what he did. I don't know if it's legal though. But in here we have x of t. So if you want the x of t, if you want to differentiate this, it's simply negative e power negative t, right? Because differentiating e power x is to e power x, e power negative has to be negative e power x, right? You get this idea. So we have this plus that. So you can, so this is what basically was done. You have negative e power negative t plus e power negative t. So this simply gives you 0. So these two, just verify that whatever you have there is correct. This is not really the solution. The solution is x equals e power negative t, and you can do that using the separation of variables. Okay, now let's go to the uniqueness of a solution. So to properly solve any linear differential equation, right, you need at least the point of the function when it's just in the first order, right, or should I say in the zeroth order, and you need so if the main differential is like power 1, then you just need these two. As the powers increase, then the conditions you need to make it to find a unique solution to it will be more, right? So let's just say for a basic linear ordinary differential equation, you just need these conditions. This is what was stated in the slide section. With the with the auxiliary conditions, right, you need it's not like they are compulsory conditions, right? So you can have an initial this one. So with the initial just like all the, let's say, he stated that all the auxiliary conditions are just at one point of the independent variable, right? So with the initial value problems, they can either give you the same points to start with. So let's say like something like this, right? This one is the initial conditions are the same, so 0 0, right? You can have boundary conditions where they give you f of 0 is this, and then f of maybe say 3 is also something else, and then that would be the boundary conditions, right? Yeah, so it's just the matter of whether you're using the same x values or different x values. Yeah. Okay, so let's move to the next thing for this one. So the next thing is the Taylor series for ordinary differential equations. So now when we say the order in this sense now, right, so this might be a little tricky. And when we say the order in this sense, now we are talking about the orders of powers of these ones, right? So this is we are trying to estimate this f of x with this function. So this one will be the 0th order, first order, second order, third order. So 0th order ends here, first order ends here, second order ends here, in that order. Okay, so we have our h being x of a. Now this is actually the same equation you've seen over and over, right? So the general expression for a Taylor series, right? So you have the summation of say f of x. So you can start from some k equals 0 to some probably to something, right? And then your then some f of x probably to some power say k, or let's say n, right? Then you have x minus a all power your n. Yeah, sorry for the handwriting. Yeah, but then I'm just trying to refer you to what we did in lecture 2. Okay, so let's just get to it. So we are writing the same thing just in an expanded form, and we are replacing the x minus a with an h. Okay, so the first order Taylor series, right? So if you are working with first order, then we would probably just use only these ones. Now there's a special name for using just these ones. We call it the Euler method, right? So with the Euler method, we have f of x equals f of a plus h f prime of a. So this is clearly a first order Taylor series. Okay, now we can write this in another form. We have yi equals yi plus h of all of that, right? So this is a function, so this will be the function they give us, and then this will be some initial point. So the idea is that the basic idea of this thing, right, is that we have this, right? We have some ordinary curve, probably we don't know, and then we have some x points. Okay, we'll probably be given some x points. Then we are going to use these x points to estimate some y point or f of x point, right? So as we are able to, the idea is that if you're able to find this point, this point, this point, so the more points you find, the more you're able to define the points that make up the curve, and with that you can get a better equation for the curve. I hope that's making sense. So let's say we have they've given us let's say like 4x values, right? And then we want to find their corresponding y's. Then in which case we end up with an xy like 1 1 to x4 y4. Now with this we can better estimate the curve, right? So that's just the whole idea of finding the using the Euler method, right? So let's try this example here. Now with this example, they've given us a function which is this, right? So 1 plus x squared, and then we have an initial condition here, y of 1 equals -4, and then they've given us x points, right? So the x points were like 1.01, 1.02, 1.03, right? x2, x3, right? This is really in the slide, so you can just check it out, right? So this tells you that your h, right, your h, which is just the difference in your x values, right, will be the, you see, the difference is even, or should I say it's equal. So you just have your 0.01, so that's your h. So that means you found your first one, right? Okay, so let's say we want the first term for this. We'll have y1 equals y0, right, plus h of the function, right, h of the function. So here, let's start with the first one. So we need our y1 equals, now we have our y0, which is -4, so you just put inside, plus our h is 0.01, right, multiplying. Now also you find that our initial x value is 1, right? So yeah, that's x equals 1, so that's our x0 actually, this is our x1. So into bracket, the function is 1 plus x squared, and our x is 1, so that would be 1 plus 1 squared. 1 squared is still 1, so you can just write 1 plus 1. Okay, then this gives us -4 plus 0.01 times 2, so -4 plus 0.02, right? Now this gives us -3.98, I guess. Yeah, right. So this is our first y value, right? Now what we do is that we now use this point. So the only point you're going to use for the calculation will be 1.01 comma -3.98. I hope you get the whole idea now. So with this, you fix this back into the equation. So now we are going to find our y2. So our y2 will be equal to y1 plus h into bracket f of x, y, right? Then so this is how it's supposed to be. Okay, you can put a times here. So here let's do that. So our y2 will be equal to our y1, which is -3.98, plus our h 0.01, multiplying our, so this one will get the 1 plus x squared. Now our x will now be this, so that will be 1 plus 1.01 squared. Alright, so we have our y2 equals -3.98 plus all of this. This one probably need a calculator. Okay, so you can just enter your -3.98 plus 0.01 multiplying 1 plus 1.01 squared, right? Then you have your next value, which is -3.959. Let's just say 960, right? Yeah, so you can just do that, you get your value. Right. But since it's also like numerical method, to see over here, it might be more helpful to write a longer decimal, right? So you can just use 9.59, say 8, 4 decimal places fine. So you can do this, right? Then your new point for your calculation will now be 1.02, right, comma -3.9598. Hope this is fine. So now let's do the next one. So using that same one, we'll find our y3 to be equal to our y2 plus h of f of x, y, right? So this will give us our y2. Our y2 is negative 0 point, it's negative 3.95980, right? All plus 0.01 into bracket our function, that will be 1 plus 1.02 all squared, right? So I'll just say, now there are actually ways to do this, right? There are iterative ways you can do this, but then I guess I just don't know it, so let's just stick to this. So we have 0.01 multiplying, then we have 1 plus 1.01 all squared, right? Then you have your answer. So we have negative let me see, sorry, I used minus here, which is wrong. So we have 0 point, yeah. So one main thing is you should know when your answer is wrong. I knew it was wrong because the answer was greater than my previous iteration, which is actually not supposed to be the case. So we have a new answer here, which is okay. So this would be our new the new point, right? So this would be basically be your x3 y3, right? And then you use this one to find your next one in that order. So depending on how many iterations they give you, so over here they give us just 3 iterations, so we just do for the 3 iterations, right? Yeah, so that's basically all for the Taylor first order, which is the Euler method. So as you can see, it's really simple. So you have yi plus 1 equals yi plus h of the function of x, y, right? So that's just all you need to know for the Euler method. That's the Taylor series first method, right? Okay, let's check what else we have. Now with the Euler method you have errors, right? So there are types of errors, 3 types of errors here. So you have the local errors. Local errors are just like okay, so as you could see, the first one I made, let me just come here. See the first one I wrote, right? I wrote this and I later decided to write this. Now if I left it like this, right, I would have made an error of 0.002. Right, I think there should be another 0, right? Something like this, right? I would have made this much error. So this one would have been my local error because of the errors we make when we are estimating the values, right? So the values we pick at every step, that's the local error. We have the global error. So if I kept that error and I worked till I got to the end, more errors would have accumulated because of that single error, which will be the global error, right? And then we have a runoff error, which is just like, let's say you are running off numbers, then you have a runoff error. Now with the Taylor second series, right, or second order, is basically the same thing as the first order, right? It's the same solution. So here let's just express it in the other way, right? So you can just have your okay, so let's say you can just have your yi plus 1, right, equal to your yi plus hf xy, right, x comma y, plus your h squared on 2 factorial, which is 2, of y prime of xy, right? Yeah, so let me see if we can get an example from the slide first. And then that I think that example in the slide actually came in the first IE, right? Actually came in the first IE. Let me see if I can find it. Okay, so this is the example in the slide. So they say dx dt plus 2x squared plus t equal to 1. And then the initial condition is that x of 0 equals 1. And then use h equals 0.01. So instead of giving you like 3 points, they just said take h to be 0.01, right? So that's just it. Okay, so that simply means that your x1 is your x0 is 0. Your x1 will most likely be say 0.01. Your x will be 0.02 in that order, right? And then the question is find the 2xt and the t2, right? Something like this. So the 2x on the 2x on the t2, right? Something like this. Okay. Then so let's just get to solving it. Okay, so from here, right? Now from here, let's see what we need. We just need a y, and then so over here, don't be confused actually, because here the y is the function, which means that this x is the y. So that's just the function. And then we have yes. So don't just confuse yourself with this. So let me rewrite it in a way that will actually go with this question. So that means that we'll have our x, right? Xi plus 1 equals xi plus h of x. We have our two variables. We have our t, right? It's just simply x of t. Oh, yeah, just x of t. And then plus our a squared on 2 all of x prime of the t again. Okay. Yeah. Okay, so this is just it, right? So how do we possibly we can just do xt, but I'm doubting with this, but then I think the t is fine. Yeah. So with this one, what we do is that we consider the functions, right? So here we need this is just a number, right? So we'll just pick it here, and then we'll always get the next one. So over here we need x of t. The x of t is, so here the function, so we'll just find our x of t from here, right? And then the x prime of t, so this is just like x prime of t, so we just have to make it the subject. Okay, so let's do that. Okay, so let's so over here we have the x, the t equals 1 minus 2x squared minus t, sorry, right? So this one becomes our first term, right? So this one becomes our x of t, right? Is that cool? And then our second differential, right? So now we have to differentiate this once. So how do we do this? Now remember, you are differentiating this, and then you have this here. So let's just do it. So the x of t, the t2 equals, now if you differentiate 1 respect to t, that simply becomes 0. Now here you can't just do this one will be an implicit differentiation, right? So implicit. So if you remember how to do implicit differentiation, is you just do 4x, right? dx dt, and then minus, if you differentiate t with respect to that will give you 1. So this is just all, right? So this simply means that will be negative 4 negative 4x. Now the x dt, we have that up, yes, we have the x dt here, so that'll give us 1 minus 2x squared minus t, right? And then we have minus 1. So you get so now this is everything we need. We just put them back into the equation, then start solving. So here, right, so our first term, that'll be our x1 is equal to x0. What will be our x0? Our x0 will be 1, right? So that'll be 1. So 1 plus, right? And then we have our h, which they give us to be 0.01. That's over here. Now our x of t, right? That's the first differential we had. So this one, right? So we can just put it inside. Okay. So well, let me just write the function so that you just don't get confused. Okay, so something like this, right? And then we have plus a squared onto a squared, that'll be 0.01 squared on 2, and then inside here now we'll have this, right? So that would be the same thing as here. So our negative 4x, right? Just this whole function, right? So you have a negative 4x. I'm trying to squeeze this in here. 1 minus 2x squared minus t, and then all minus 1. Okay, that's fine. Right. So now so if you have to put in your values, you have your 1 plus 0.01 multiplying 1 minus. Now don't forget, this will be your initial x, right? What we did up there, that's just 1 minus 2 times 1, right? That's 2 times 1 squared, that's 2, right? Minus your t. Our t, the t we are starting with is 0, right? Because we are doing here, so that will be 0. And then we do plus 0.01 squared on 2. I don't know the value for that. Okay, and then we have multiplying negative 4x. Our x is, like I said, our x is 1, right? So that'll be negative 4 into bracket 1 minus 2x, there's still 1, so 1 minus 2 times 1, which is still 2, right? Minus rt, which is 0. You close this bracket, then you bring your minus 1, right? So that means that our x1 will be equal to, when you enter this into the calculator, you can just do it at the end. You get 0.9901. So this will be your x1, right? Now what we are going to do next, right? So this is what you do next. So what you do next is you pick your t1 x1, then you start the whole process again. So you see we started with t naught x naught, right? So our t naught x naught, so our t naught was 0, our x naught was 1. Now we are defining a new point, so our t1 will be an addition, right? An addition of the previous one, which will be your, that'll be your 0.01, right? So that'll be 0.01, and then your x1, which is a function, that will be 0.9901. So 0.9901, right? Then you do the same thing for your next one. So that means you have your x2 equals your x1, right, plus h of 1 minus 2x1 squared minus t1, all plus your h onto your a squared onto, sorry, into bracket your 4, so minus 4x1 into bracket 1 minus 2x1 squared minus t1, right, and then all minus 1. So this is going to be your second one, right? Then so let's just do that. We can do it. So you have this one, which will be 0.9901 plus 0.01 multiplying the, that'd be 1 minus, so we have this, right, 2, so 2 times 0 point this one squared, right? So we just have 2 times 0.9901 squared minus our t1, so the t1 will be 0.01, okay? And then this closes, then we do plus 0.01 squared on 2 factorial, and then the next one, right? Then we have minus 4x, so minus 4 times 0.9901, or multiplying 1 minus 2 times 0.9901 all squared, right? And then minus our t1, The t1 is the 0.01, right, or minus 1. The minus 1 is outside, right? And then when you punch this into your calculator too, you get your x2. So your x2 will be 0.9716. So this means that this is how your values will look like. So now you see we've given t0, x0, t1, x. So you have your t2, x2, right? So now your t2 will be your 0.02, right? Because it's an addition of the h. And you have your x2, which is 0.9716. Now if you're asked to do more, then you use these ones to find your next one. So you can just find an x3 and x4 depending on the number of iterations they've asked you to do, right? Okay, yeah. So when you check in the slides, it's just the same thing. So this would be your, so if they asked you to do like 3 iterations, then this would be your final answer. Yeah, and once you solve these procedures, just try to remember that most likely he might just bring the same thing from the slide, and then it will be at your advantage. Yeah. So this is all for the first one. So I'll just make another video for the Ranjikata. Alright, thank you.